Okay, I've uploaded today's slides for, we're going to start syntax today. The slides are in that list in Moodle. If you'd like to take notes while I go through the slides, could you please check if you can access those slides? And we will start with questions about that last lecture that I couldn't come to because I had a small accident on the way. And I hope you were able to, I uploaded the slides with basically what corresponds to a script there. I added a lot more text that it would have been otherwise. Do you have any questions about the slides on modeling parts of speech, or basically modeling sequences for parts of speech using hidden Markov models? So yeah, I can briefly go. Yeah, okay, good. Not yet. Anybody else? So you can switch to the slides in the, if nobody else has questions, is the procedure with a trolley clear? Because this was what you will need for what you need for the implementation. The stable procedure with a trolley and collecting the probabilities through along the paths. Okay, if there are no questions, I will just move on to grammars. If you still have questions at some point, just ask questions. Can you ask questions using a microphone? I think so. I think so. Okay, so let's switch to, let me see if that slides are, oh, these are wrong slides. Why is it doing it? Sorry, you have wrong slides under grammars and parsing, but I'm going to fix it in a second. Why is it doing it? Oh, yeah, exactly. There are two PDF files, and then it sees only the first one. Okay, now you should be able to see the, yeah, now you should be able, let's check. Yes, so the slides that are linked now under meeting on June 10th, grammars and parsing. One is today's meeting, and we're going to switch to that. Okay. Make sure. Yeah, so you have exactly that set of slides already in the list. It's in the list in Moodle on the front page of the course, and we can start if there are no questions. Okay, so we're going to start today two sets of meetings. This is the first of the two meetings on grammars, on syntax in general. We talked about words, but of course, natural language is about building structures that are more complex than words to be able to express ideas. And those structures are built according to certain rules. Every language has different rules for building complex structures. Some of those rules are shared, some basic rules are shared, but a lot of the rules are not shared across languages, but they may be shared within a language family. And this area of linguistics that deals with the description of structures, complex structures in natural language is called grammar. And in case of formal approaches, very often you also see instead of grammar, we talk about syntax, syntactic formalisms. Syntactic formalisms describe language structures formally, but what you know from school for sure is grammar. And grammar is as this picture here illustrates, about identifying the structural distinctions within language structures that contribute to change in meaning, as it's illustrated in this sentence. So your here the possessive pronoun, and you are here this contracted construction of the pronoun and a verb, of course, dramatically change the meaning of this phrase. Even though phonetically they are very close, and actually these two, your and your, are so-called confusable words in terms of pronunciation. They are very close. They could say they are near homophones. Okay, so syntax is about describing sequences or larger structures of language. And typically, we describe sequences of words that make meaningful sentences. And very often, you can tell whether a sentence is potentially meaningful by looking at its structure. This is a good indication of whether a sentence is meaningful, not always, of course. So if you take this set of words that we have here, Sun, Leipzig, the, shining, warm, in, you can form various strings out of this set of words. The first one, the Leipzig, shining, warm, the sun, maybe there is some meaning, but doesn't seem to be clearly identifiable at first shot. In Leipzig, warm sun, the shining, probably a non-native speaker could produce something like this, but and you could probably guess some meaning what the non-native speaker might mean, but this is not a valid structure of English. Warm, the in sun, shining is similar. Again, a non-native speaker might produce it, but the valid structure in English is the sun is shining in Leipzig. And this structure, by analyzing the structure, basically, the meaning of the sentence can be interpreted. And this is done because we compose the meaning of the whole by analyzing the meaning of its parts. This is a very strong observation that the meaning of the whole is the sum of the meanings of its parts. Of course, it doesn't always hold. There are phenomena in language that clearly indicate that you need more than the meaning of the parts to identify, to interpret the meaning of the whole. And one example of this could be, for instance, demonstrative pronouns. If you say, the sun is shining there, and you use the deictic pronoun, so a pointing pronoun there, of course you have to know where the there is. And just by knowing the meaning of there, that it's a deictic pronoun pointing at something, you don't know yet where it is that the sun is shining. So Spraguean observation about the composition of the whole being a sum of the parts is it's not enough for some language phenomena. Okay, so let's look at the definition of what we are going to talk about here. We're going to talk about syntax, so about principles and processes by which sentences are constructed in specific languages. This is how Chomsky defines syntax. And we can talk about syntactic structures of a single language, for instance, German, English, or language families. This might be, you can ask questions such as what elements are part of this language, how they are combined. We can talk about the grammar of a single language. The grammar is about certain features of a language and how those features contribute to producing well-formed sentences. So for instance, some languages possess marking on certain word classes. We talked about word classes already. For instance, in German, In German, as well as in English, nouns are marked for number. So nouns can be plural and singular. Verbs in English are marked for, as well as in German, are marked for features such as tense, such as person, and also number. So these are features of individual word classes that contribute to that contribute information to what forms valid structures. You can't combine, you can't put certain words together if their features don't, in colloquial language, match. Grammar can be formalized, so a formalized model of a grammar will be rigorous descriptions of rigorous description of what forms valid utterances, valid sentences in a given language. And we are interested also in conditions on grammaticality. So for instance, what I was just talking about, which structures are licensed due to certain markings or certain features on some elements that license and or maybe not license certain constructions. There is this concept of universal grammar that Chomsky introduced, or the hypothesis, let's say, that there is some related to the fact that language is the most basic kind of human activity, communicative activity. And so the hypothesis is that there must be something universal across languages that underlies all languages, that contributes to the human linguistic ability, human communicative ability, communicative in language, of course, in general. And the assumptions that underlie this universal grammar hypothesis form a basics and also, in a sense, limits of formalization. We're not going to go into details of this. If you're interested, Chomsky is a classic. Chomsky also, the early books, they don't read very well, but his later books are written in not as dense language. But if you're interested, I strongly recommend to read some of Chomsky's classical papers, because these are classics. I think people should read something by Chomsky if they are interested in language. The syntactic description of language is based on some fundamental properties of language in general. And these properties of language, of course, form or build up requirements on the formalization, so on the syntactic description. In particular, we have three basic requirements, or also to some extent hypotheses on how languages are constructed. I'll get to the third point that is somehow represented more strongly with some grammar, some approaches to grammar, in particular Chomsky's approach. But the most basic principle and requirement on the syntactic description is that language basically is a sequential process. It's language is produced sequentially. Words come out one after the other. There's certain temporal linearity to language production. And they can be only perceived in this linear order, in this sequential order. Another observation, important observation that we immediately see of language is that language exhibits ambiguities, in particular also syntactic ambiguities. And what you have here is a rather famous sentence attributed by Chomsky. Flying planes can be dangerous. This sentence is ambiguous at many levels. You're welcome to figure out how it is ambiguous. Think about it a little bit and think about what contributes to this ambiguity and what potential problems for NLP these ambiguities illustrated in this sentence can produce, what problems they can produce. And the third very strong hypothesis is that language has certain hierarchical properties. Language structures are structured, are built up in a hierarchical fashion. So these hierarchical nature or nature, it's not clear whether it's nature, but the observation on the hierarchical properties of syntactic structures. Like I said, it's a very strong assumption in some grammar formalism. For instance, in Chomskyan approach to language. This is also a strong hypothesis on the representation of language in the brain. So the hypothesis is basically that this observation on hierarchical structuring of phrases, for instance, sentences, has a core in the way has its core in the way language is represented in the brain. Of course, this is very hard to verify. This is this kind of slogan that you say that you might hear that linguists like thinking that we have little trees in our brains because these structures, the hierarchical structures that language exhibits, is basically a tree-like structure. Of course, it's rather hard to tell, hard to even imagine how one would verify this hypothesis. But for sure, this hierarchical structure is rather obvious that it's an appropriate way of looking at language. It can be illustrated here. It's illustrated here by an analysis of this former sentence. You see that some phrasing, some segments that we might identify in this sentence do not form well-formed larger structures, so well-formed chunks or phrases, we will call them later. Flying planes is a valid structure if you think about this as a noun phrase. Flying planes is the activity of making planes fly. However, it can be also a structure that describes planes that are currently flying. So here is the head of the noun. These are the airplanes, and flying describes the activity that the airplanes are currently performing. Can be is a valid structure. It is a verb that is modified by a modal verb that introduces the modality to this main verb. However, this chunk here, planes can, doesn't form a valid syntactic chunk on its own. There is potentially no interpretation that would say, okay, can be considered a noun. Can is basically this metal container, but saying that okay, planes is modifying this noun can. This is a rather long stretch. It's rather clear that this segment here is has no meaningful interpretation, and the process of identifying these meaningful segments, these meaningful smaller units, is helped by, can be helped by various tests for determining what is a valid segment. You see a word constituent here. We will get to that. Those valid segments will be called constituents, and there are various empirical tests that help determine whether a segment such as this one or this one is syntactically valid in a given language. These tests are looking at various operations that one could perform on a given chunk to see whether it's still valid in a different lexical context. Okay. So this is syntax. Syntax is about putting words together. What is grammar? Grammar is part of syntax and this study of syntactic structures in a language. A grammar is a description of valid structures of a language. So grammars you're of course familiar with. You must have written at least one. In programming languages, you write grammars um, probably for parsing some types of document. You have to describe what valid structure is. For instance, you could think about producing a grammar of an XML document. This would be an example of a grammar. Of course, natural language grammars describe natural languages, and natural languages to some extent can be exhaustively, not always exhaustively, formally described. But and this formal description, formal grammars, is basically what formal linguistics is about. A formal grammar is defined by a set of rules that consists of as in formal grammars that you've seen in programming languages, of terminal and non-terminal symbols. Those terminal symbols in case of natural languages are words. Words cannot be rewritten any further. Of course, you can think about languages that exhibit strong inflection. You can ask then, well, what is a word? Is the word, remember, words can be analyzed further into smaller units. What is this terminal symbol? Is this terminal symbol the root of the word, or is it the terminal symbol all the individual inflected forms of the word? This is a very good question, and different grammars approach this question in different ways. And non-terminals express clusters or generalizations of terminals. So these larger units, we saw examples, valid and non-valid examples of those larger structures in the previous slide. And these will be the constituents that will be put together in the course of forming sentences. Formally, grammar, of course, is this tuple here that consists of an alphabet. So the terminal symbols. In case of natural language, our alphabet will be the alphabet of words. Of course, alphabet is an abstract concept here. A finite set of non-terminals, a start non-terminal symbol, and a finite set of production rules. In the case of natural language, this will be production rules of that produce valid natural language structures. You may have heard about so-called Chomsky hierarchy, types of formal grammars that Chomsky defined. The hierarchy describes grammars in terms of their complexity and their properties. The most basic kind of grammars are those that exhibit, let's say, the simplest rules. So at the core are so-called regular grammars. We will briefly look at regular grammars in a moment. They only exhibit rules where you would rewrite non-terminals into non-terminals. Context-free grammars will be those grammars where the rules do not depend on any prior context. So the left-hand side of the rule will only be a non-terminal. Context-sensitive grammars will allow for a non-terminal to be a restriction on the left-hand side production of the grammar, and recursively enumerable rules will model any kind of production that is possible with this with the rules of the form described here, basically. So regular grammars and context-free grammars are those that are typically used in NLP. Many parsers are used on these two types of grammars and their expressive power of those grammars. There are also grammars that are context sensitive, which model some phenomena of language that these two cannot model due to the restricted nature of production rules. But for the most part, we will mainly stay within the realm of regular and context-free grammars that generate regular and context-free languages. Here is an example of a context-sensitive rule production, just to illustrate this. A context-sensitive grammar will have productions of this type, where here you see both terminals and non-terminals on the left-hand side. So this kind of grammar can describe languages of this form. We will not go into details of this, but you are welcome to analyze in more detail what context-free grammars, context-sensitive grammars, and regular grammars, how they differ and how these production rules differ. And I'm assuming that you have seen, we will focus, like I said, on context-free and regular grammars, and I'm assuming you've seen these concepts in your other classes. Is this the case? Could you just confirm whether you have seen context-free and regular grammars in probably programming languages or, yeah, exactly. So, exactly. So this is just a reminder. Maybe you haven't seen a context-sensitive, an example of a context-sensitive production system. This is in the 2 slides earlier. Like I said, most frequently used formalism in NLP is the formalism of with the expressivity of regular grammar, so regular languages, because a lot of the types of linguistic structures that we describe in NLP have sufficiently restricted properties that they can be analyzed using the expressivity that regular grammars provide. Examples of such entities, linguistic entities that can be described using regular grammars are, for instance, numeric entities of various types, numeric and alphanumeric entities. For instance, quantities, proportions, ranges, time date expressions, phone numbers, or monetary values. All these can be described using regular grammars. Here are examples of a time expression, date expression, monetary expression, or some phone number expression. These expressions are typically modeled using set of rules. It's basically just not necessary to build systems of a higher complexity for structures of this simplicity. And approaches based on regular grammars are very often used in various types of various extraction types. Sorry, I clicked various information extraction tasks. Yes. Oh yeah, now it clicked correctly. A little more interesting are context-free grammars, which regular expressions, of course, will not cover natural language sentences, or we could say they would cover a very small subset of natural language sentences. However, context-free grammars, just one level higher up in that Chomskyan hierarchy, context-free grammars can describe a good portion of natural language sentences in some languages. Of course, in complex languages that exhibit complex linguistic phenomena at structural level, this will not be sufficient. But for English, for instance, a good portion of English can be described with context-free grammars. And context-free grammars are particularly useful in the sense that they very transparently encode this hierarchical structure of the linguistic units. There are also probabilistic extensions of context-free grammars, which add probabilities to the structures to describe how likely they are how likely they are to. Sorry, my phone is just making noise and distracting me. Sorry about this. I will switch it off. Sorry about this. which capture probabilities of in terms of how likely a given structure is to occur in language, and these probabilities can be derived from corpora, for instance. And context-free grammars typically are used for basic syntactic parsing. And this concept of syntactic parsing should be actually clear too. Rather self-explanatory, is a type of text analysis that determines the syntactic structure of a sentence. So in comes a sentence, out comes our famous tree. This is an example of a sentence. Again, linguists like these kind of convoluted or counterintuitive, unlikely sentences, such as fish people, fish tanks, which can have some semantic interpretation if you really try. But for most people, it would be just weird. But linguists like these kinds of sentences. And exactly this hierarchical structure is what the phrase rules, so the rules for forming phrases or constituents in natural language will be written into the productions of context-free grammar. So for instance, you could say that a noun phrase on the left-hand side is a structure that consists of a noun and a noun. So on the right-hand side, you would have these two symbols, non-terminal symbols. In the production rule. Similarly, you could say that a verb phrase, so a VP here, would be on the left-hand side, and on the right-hand side of a rule, you would say that, okay, a VP is a form of a verb followed by a noun phrase, so by an NP. Another rule would say that a noun phrase on the left-hand side of the rule basically consists of a noun, and it zoomed in, I don't know why, yeah, of a noun. So these would be an example of a non-terminal rule with non-terminal symbols. Of course, you would also have rules that consist of non-terminal symbols leading to terminal symbols. So an example of a rule, such a rule here would be one that says that this noun can be on the left-hand side, on the right-hand side would have this word tanks here. Okay, key to the language description, and specifically to describing well-formed or valid linguistic structures, are two notions. The first one especially is important in looking at what constitutes a valid structure of a language. And this notion is the notion of constituency. And a constituent is a word or a group of words that can function as a single unit within a hierarchical structure. So you could think about it as constituents being self-contained units that you can replace with other units as a whole, independently now of whether they would form a meaningful sentence. But an example here, you could say, of a constituent is a noun phrase. So the difference here is a noun phrase that can be substituted with a different noun phrase. It would be still a valid sentence grammatically. Whether it makes any sense is another story. We'll get to semantics later. We go step by step. For the moment, things may not even make sense semantically. It's important that they make sense syntactically, structurally. Another constituent is a verb here to understand. This verb, of course, here is part of a noun phrase. Here is the full constituent, the full verb phrase, to understand the difference. And again, you can say, okay, in a context where a verb phrase with an infinitive is required. So some verbs, such as try, require verb phrases in an infinitival form. This whole constituent, this whole verb phrase could be substituted. We try to understand the difference. We try to get home. We try to do our homework. We try to pass this course. Yeah? So these are constituents. They are words or group of words that are, in a structural sense, self-contained. They can be they can be they can function on their own. And constituent structure of a sentence models the constituents or phrases of a sentence and how they are put together out of other constituents. As you can see here, this verb phrase constituent VP consists of other constituents of this bear verb phrase, and understand the difference, and the noun phrase is also part of this constituent, the difference itself. Constituency parsing then, of course, will refer to identifying the phrase structure of a sentence. So we talk about constituency parsing. Sometimes you will also hear phrase structure parsing or phrase parsing. It's all referring to identifying these hierarchical substructures of a sentence. Those substructures, where those substructures can are in a syntactic sense self-contained. Another important notion in syntax is the notion of dependency. Dependency is a notion that will also appear in semantics later, and this is an this notion models yes idiom dependencies between the words in a sentence. Dependencies are not so much about the phrasal composition of a sentence. It's more about, it's closer to syntax, you could to semantics, you could say. It rather models the high-level view on which elements are subordinate or and superordinate with respect to others in terms of certain syntactic dependencies. So you have an example here of that same sentence. Now being, you can see you can see this right branch here. In terms of dependency, in dependency, you ask what is the more important unit in a given phrase, and what is the subordinate unit. The more important unit would be the superordinate unit, so the root of a given tree sub-element, and the superordinate and the subordinate unit would be a leaf of that tree. The root, of course, every sentence, every tree of this type has to be somehow rooted somewhere, and typically the root of a dependency structure will be the main verb in a sentence. This is again sometimes not the case, or some formalisms define dependencies in which they introduce a kind of dummy root to which the main verb is attached. So it's basically hanging from something like a sentence root node. So the main verb in the sentence here is try. We try to understand the difference. The main verb is try. Try has a subject. The subject of the sentence is we. So it's you could say that the head of the sentence and the head of that dependency substructure is try. The dependent is we. The dependent sub-element of the verb phrase dependent on try is understand. The verb understand will not be could also be the head of the whole tree, were it not for the fact that we have the verb try here. Of course, we understand the difference could be also a valid sentence. Then understand would be the head of the structure. In this case, it's subordinate with respect to the main verb try. Again, subordinate to the verb understand is this preposition here to. This is only a structural element in a sense that the fact that to is represented in the sentence is only due to the fact that try requires verbs with in an infinitival form. So in a syntactic dependency tree, we would represent these structural elements. As you will see later, we will not be representing these purely structural elements, purely syntactic artifacts, you could say, in a semantic representation. Another dependent will be difference here, the noun, and further subordinate is the article itself. Again, in the semantic representation, we will not be representing the purely structural elements such as this determiner here. Do you understand the difference between constituency, between phrases and these dependencies? Where phrases are really, you could say, linear, sequential, sub elements of a sentence which form valid structures. And here we build a tree directly from the by finding the subordinate and superordinate elements in a tree. Do you see this? Do you understand this difference? It's a rather critical difference because parsing approaches will also differ with constituency structures and dependency structures. This is closer to semantics, and this is really just the structure. Yes, we'll get to that, how it's going to be used. But I hope you see that this structural dependency here is closer to modeling semantic dependencies between the elements of the sentence. So if you forget these structural elements such as to, imagine this to is not there, this the is not there. If you take only this part of the tree, I don't know if I can draw here. Probably not, or maybe I can. If you take only this part of the tree, yeah. If you take only this about models, you could say what the sentence means. We don't need this to know the meaning of the sentence. Oops, sorry, zoomed in. And we don't really need this to know the meaning of the sentence because these are structural elements and they only are there because the English language, the part of the grammar of the English language is that nouns are preceded by articles. Some other languages do not have articles. For instance, Polish, Slavic languages do not have articles. To is a structural element that is only there because this verb try requires a verb in an infinitive form. But the meaning is in this verb here, and this to is only an artifact. It's a syntactic artifact. But the meaning of the sentence is pretty much described or contained in this part of the dependency. So the dependency models structural hierarchy between elements that is quite close to what is needed to identify the semantics. Whereas from these structures here, it's rather not so straightforward to say how I would get from these. Of course, there are methods to do it. And one such method is, for instance, Montague grammar that says, okay, we're going to combine these elements of this noun phrase here in such way that we will have a semantic representation that will describe the meaning of this, or formally describe the meaning of the noun phrase. This formal semantics that is used for the description is semantics that is the formalism of lambda structures. You use a term language with a binder-based term language can which allows to combine the individual terms into larger constituents. So you could say that, of course, you could compose the meaning of the whole sentence by combining these phrases as well. But the semantic dependency of the individual constituents is not highlighted here at all, whereas here it's explicitly is pretty much explicit. Okay, we'll get to how it's used, how it'll be used later. But the key point is that the dependency will be closer, can be used more immediately to analyze the meanings of sentences. And this is what I was trying to show with that little tree. Okay, constituency, however, is good for talking about things like what is the right structure, which elements form right structures, and how they are combined. Like I said, there are tests for constituents. So what is the right structure, or license structures? And one example of such test is a substitution test, and specifically a test for pronominalization which asks can a phrase be substituted with a pronoun? If it can, then it probably was a constituent. So here is an example of a sentence. The streetcar was stopped by the collision with a car on the intersection of Augustus Platz. Sorry for my German. You have the noun phrase here, the streetcar was stopped by the collision with a car and on the intersection of Augustus Platz. If you ask what the constituents are, and if you want to use the test, you ask basically, what can I substitute with a pronoun? And it turns out, well, you can substitute this noun phrase, the streetcar, with the pronoun it. So it was stopped by the collision with a car. We also substituted by the collision with a car can be substituted by a pronoun. Okay, never mind that the meaning will be lost, but the substitution is possible. And on the intersection of Augustus Platz can be substituted with a dictated pronoun there. So all of these, you could say, are valid constituents. Whatever can be substituted with a pronoun is a valid constituent. There are also other types of tests for constituents. There is a Wikipedia article on constituents which lists those tests: a topicalization test, coordination test, whether you can put the two things together, whether the segment can be topicalized, so whether it can be put to the front of the sentence. We will not go into details of those here in the slides, but you're welcome to look into this Wikipedia article and check out the other tests. The main point is that a constituent is a structural unit that can function on its own, and you can test whether some segment is a constituent by asking, for instance, whether you can substitute it with a pronoun. Of course, there are also other tests that will tell you that how to test verbs for constituency. So you can look at those in the Wikipedia article. Because of course, not only noun phrases are constituents. And the second question, what is the right structure in terms of constituents? Well, the right structure is determined by production rules. So here you have examples of production rules for English. A sentence is something that consists of a noun phrase. I hope you understand this kind of notation with an arrow. Left-hand side is an antecedent of a rule, and the right-hand side is consequent of the rule. So are you familiar with this notation, or should I explain the notation? I think this is a fairly standard notation. Okay. So a sentences, yeah, this is also, I think, used in where in programming languages you work with context-free grammars. Yes, exactly. Yeah, this is related, a very good observation. Some languages can be represented, can be produced by automata of different complexity. Very good. So a sentence would consist of a noun phrase and a verb phrase. A noun phrase will consist of an article and a noun. A verb phrases are complex. Here's just one example of how verb phrases can look. A verb, a noun phrase, and a prepositional phrase. And a prepositional phrase here consists of a preposition and a noun phrase. And here is a sentence that is described exactly by those rules. The carpenter drives the nail into the beam. Here is our noun phrase consisting of article and noun. This is this rule. Our verb phrase is here. This is a whole verb phrase. And let's analyze it bit by bit. Here's this last part, the prepositional phrase consisting of a preposition and the noun phrase. So this is the PP, consists of a preposition and a noun phrase. I'm sorry about the little mess up here. You have the P here. This is non-standard. And if you were diligent and study the tax sets, you would know that in the pantry bag tax set, this would be in, and this is what we had in the previous slide. I'm sorry, I'm going to fix this inconsistency later. Here is our noun phrase consisting of an article and a noun. Here is the rule, and the verb phrase finally says that the verb phrase consists of the verb itself, the noun, and the prepositional phrase. Well, here's the rule. So you could say that constituents are defined by the rules of the grammar, basically. What are the problems with this approach, with this phrase structure grammar approach? There are many. Not all language isn't art in pen, actually. Yes, that's right. Very good. This is also a little inconsistency in the slides, and this is because this slide was inserted only recently. Even here, there is a little inconsistency with the pantry bank notation. But I mean, these are just labels, actually. This could be DT, this could be dead, or it could be booms or bings or whatever. So yeah, but in pantry bank, of course, it would be the labels for the different word classes would be different, or parts of speech would be different. So what are the problems with phrase structure grammars? There are many. Phrase structure grammars will not be able to describe all phenomena of many languages. Especially problematic are languages with a more relaxed word order. And German is an example of such a language. Some language phenomena of German do not lend themselves to modeling with phrase structure grammars. One example of this is this verb second phenomenon in the German language, where the verb occupies the second position, and in particular with verbs which consist of a preposition and the main head verb. This head would be put in the second position, and in some syntactic contexts, the preposition would be put at the end of a sentence or at the end of a constituent of a clause, for instance, and this cannot be modeled by a context-free grammar easily, or some context actually cannot be modeled at all. Thematic roles cannot be modeled by context-free grammar. Some congruence phenomena, so some agreement phenomena. Congruence is just a fancy word to describe um, the fact that features of linguistic elements have to match, so have to be congruent. Uh, uh, cannot be easily modeled with context-free grammars. Of course, there are extensions that to phrase structure grammars. So phrase structure grammars are the kinds of grammars that I showed you here. This or this, basically. These phrases here in constituencies that describe constituents. Cannot be modeled in phrase structure grammars. And there are, of course, alternatives. Some of those phenomena can be modeled with dependency grammars, but some phenomena lend themselves better to more expressive linguistic formalisms. An example of such a more expressive formalism is HPSG here, head-driven phrase structure grammar. So you see that it is a phrase structure grammar, but it's augmented by information about so-called head principle, morphological dependencies, and at large, every word is modeled in this grammar. There is a set of rules, as in phrase structure rules, but every word in this grammar is modeled as a complex sign, which includes features on the given word. For instance, for nouns, it would be number, gender, and so on. And these features are then unified when production rules are processed, combined, basically, using a standard unification mechanism. We will not get into detail of these more complex grammar formalisms. I will only show them. I will show an example also of an HPSG in the next lecture when I talk about approaches to parsing. Okay, I have to probably hurry a little bit. I will skip some of this transformation approach. And I will get back to that in the next lecture. And we'll move on to regular grammars, which I will also only skim over because most of it is what you know from other courses. I saw a question. Okay, not a question. Yeah, sure. Not a problem. The slides are on online. So I will only skim through regular grammars because regular grammars, like I said, I'm assuming is part of another course, and I'm assuming you're familiar with regular grammars. Regular grammar is a type of grammar in which all the rules are of this form. So they do not have any context on the left-hand side. The U is an element from a non-terminal, and the V is either an end element, a non-terminal, or a terminal or a non-terminal. The sigma is the alphabet here. It's the signature of the grammar, or signature of the grammar, or in our case of natural languages, this will be the vocabulary. And regular grammars, as you know from automata theory, can be represented by finite state automata. Regular grammars can be represented by regular expressions. And regular grammars are actually very often used in NLP. These automata approach to modeling various language phenomena is a rather old school traditional approach, but still used for some phenomena because it's sufficient. For instance, morphology is very readily modeled by finite state machines. So this finite state approach to morphology, so to the composition of individual words, is still well-performing approach to modeling word formation. I will skip the theory of automata. This was in the other course, but it's here for the record. Regular expressions you're also familiar with, and you should be able to, we're going to assume that you can build basic regular expressions, and you should be able to do it for the exercises. Regular expressions are very frequently used in NLP, particularly for some expressions with predefined structures. I showed examples of those already earlier. Very often they are also used to describe features of which are then used as in machine learning, so extracted from natural language elements and used as features in machine learning. I will not go into the details of regular expressions. I'm assuming that you are familiar with this notation, and in particular with these meta characters for regular expressions. If you're not, then they are actually explained in the slides, but I will not go through them in the lecture. I'm just going to ask you to go through these slides at home. And the oh, sorry about this. I'm just getting to where the end of regular expressions section is. Okay, it's here, regular expression modeled as automata. All of this is familiar. I'm going to skip through this and yes, get to an extension of context-free grammars with probabilities. So with the model of how likely a given substructure is to appear in a language, which can be used in parsing. So this is just a recap on what phrase structure and so constituency tree and what a dependency tree is. We talk about structures of this form as we refer to them as constituency trees. We refer to these kinds of structures as dependency trees or dependency parses or constituency of phrase parses. An extension of a phrase structure grammar with probabilities will do nothing else but assign additional probabilities to each of the production rules. So how likely a production rule is to appear based on some corpus. So in a standard context-free grammar, you will have structural rules of this form, binary, unary form. So this is a binary rule, this is a unary rule, this is an empty rule, binary in the sense that in the right-hand side, the consequent of the rule, you have two new non-terminal symbols. So it's a binary branching structure that results. This is a unary branching, so a single branch that results. In parsing these kinds of rules in a standard context-free approach, before such a grammar can be applied, typically the grammar will be transformed into, into a so-called Chomsky normal form. This is um, a transformation of the grammar production rules that will lead to a more efficient parsing, basically. And this Chomsky normal form um, is built according to a predefined set of rules. First of all, this transformation, and R is missing here, sorry, I'll fix that, has as its goal binarization of rules, so transforming all the non-binary rules into binary rules. For instance, here, this is a non-binary rule. We want to split it up into two binary rules. We do it by introducing new non-terminals. There will be some cleaning of the rules. We will remove recursively empty rules and unary rules. So for instance, sorry about this. We don't want a rule of this type as here. This is an empty rule. But the transformation is such that it doesn't change the language that's generated by that grammar. It only results in different trees, for instance, because we introduce these new non-terminals to split non-binary rules. So, like I said, why we do this transformation is because this transformation leads to more efficient parsing, and this is the main reason. This cleaning is non-mandatory, but it again makes parsing quicker and cleaner. And the grammar is in fact, these empty rules are not are empty rules, are non-relevant for the grammar. There is a pseudocode for removing non-binary rules and empty rules here. I will ask you to go through this pseudocode, so this transformation of a grammar to a Chomsky normal form in detail at home. And I will just give you an example, a walkthrough example, using an example grammar. What we are doing basically, but please go through the pseudocode yourself. We do the following steps. First, we transform the grammar so that we introduce a new start symbol. We remove all the new productions, null productions, by finding all non-terminal variables which derive an empty string. We don't need those. For each production of this type, where all productions were obtained from this rule, we remove all the empty rules again, as in the first step. This is basically a recursion to remove all the empty production, this step. Then we remove in a similar fashion all the unit productions, so all the unary rules. Again, in the same fashion pretty much as in empty rules. And we delete all those unary rules until it's also done in a recursive loop so that all the unary rules are removed. We replace all the productions with which are non-binary by introducing a new symbol. The symbol will be here. You see, if you analyze it in detail, such that there is only one or so that there are only two non-terminal symbols on the right. This is done for all productions with two or more symbols on the right. And finally, there is also a rule for replacing unary rules with non-terminals with rules with terminals. So in the end, this will proceed for our grammar as follows. Here's our empty empty string or empty production and our unary production. Here is our ternary rules, and we would want to, from this, we'll have to produce several new rules for every unary production. We will add new rules to the grammar. This is illustrated here. So this grammar is larger. And for every ternary rule, we will also, replace these ternary rules with additional rules by introducing additional terminal symbols and introducing new non-terminal symbols that were not originally in the grammar. This is done here. And exactly, and this is done here. Here's our new non-terminal symbol that was introduced to replace this ternary rule that was here. And look, in the meantime, we introduced so many new symbols to the lexical rules. All of these were not there. This VP was not there. This S was also not there. But finally, what we have on the side of production rules is exactly what we want. Every single rule consists only of productions which result in binary branching. There are no empty productions, and there are no unary productions. So what we have as a result, the kind of tree that this grammar will produce will be a binary tree, basically. With the probabilistic context-free grammars, the general principles of the grammars are the same, but each rule is accompanied by a probability. Again, for parsing, the grammar should be transformed into Chomsky normal form, or at least, binarized. So this is a principle, a requirement for parsing. But every rule will be accompanied by a probability. So this rule has a probability 1. It's always the case that a sentence consists of a noun phrase and a verb phrase. This rule here, that a verb consists of a verb and a noun phrase, has this probability. These are made up, of course, in this example. This kind of rule, this rule, ternary rule, has a probability of 0.4. And these probabilities, where they come from, is a corpus. What you need to find these probabilities is a corpus of phrase structure trees where basically each sentence has been analyzed in terms of phrase structures. And you can read off the likelihood of such a subtree appearing in the corpus and build and add it to the probabilistic context-free grammar based on that corpus to parse sentences. Whether it will generalize is another story, but the key concept of probabilistic context-free grammar is basically that a rule is accompanied with a probability. And now parsing consists of collecting all these probabilities in the standard fashion, so by multiplying them out. But a good side effect of this is that now you can have a likelihood of a given substructure. Yeah, so you could say that the likelihood of this substructure appearing, okay, again, modulo the corpus based on which you derive the probabilities, is 1. The probability of that substructure is 0.4, and so on. Of course, with different structural interpretations of that sentence, and this is what is illustrated here, based on this ambiguous sentence, people fish tanks with rods. In this case of this sentence, fish is the main verb. And in case of this sentence, in case of this sentence, fish is the main verb, and in case of this sentence, you have this noun phrase with a prepositional phrase describing rods as being an instrument for fishing, whereas here those tanks are accompanied with are accompanying by some rods. Yeah? So do you see the difference between this here being an instrument for fishing? The main verb is fish. People fish tanks, and they use rods for fishing those tanks. Whereas here, people fish, and what they fish is tanks with rods. You see it because here, the noun phrase is this, whereas here, it's this. Okay, so maybe this second drawing is a bit awkward, but it's something like this. So here we fish with rods, and what we fish are tanks, and here we fish tanks that have some sort of rods. And you can calculate the good side effect of parsing with a side effect, a good additional information that we get from probabilistic context-free grammars is that we get a likelihood for this interpretation being whether this interpretation is more likely than this interpretation or the other way around. And here, this phrase structure 3T1 has a final probability of which is not very high, but it's still higher than this other one where the tanks have rods. So fishing with rods is more likely than tanks with rods. Okay, and finally, I think I can start here in the next. No, I will not start here, but this I will need for the next session. So I think we could stop. This is a good place to stop. Are there, what time is it? Okay, we still have time for questions. Are there any questions? Because I think I would like to add this to the next lecture where I talk about the different approaches to parsing, and then I'll go into details on dependency relations. The new exercise is for next week. Which new exercise do you mean? Do you mean the exercise on HMMs, or do you mean the exercise that will be released tomorrow? The one on HMS, I think it's due. It should be due.
Yes, HMMs is due next week. I think it says so in the exercise sheet right at the top. So we will meet tomorrow to discuss the words 1 exercise, and we will meet next week to discuss the HMM exercise, the words 2.
Yeah.
It's 2 weeks for this exercise, isn't it?
Yeah.
It is the whole of this week and the whole of next week until you have to submit the HMM one. So that's 2 for me.
Yeah. So I don't know actually when was the HMM released. It was released on Friday. It was released on last Friday, right?
I think it was released
or on Monday.
Sunday.
Something like that, yeah.
Sunday.
So it is 2 weeks. Yeah, so it's in fact 2 weeks. Yeah, okay. Yeah, it's clear. Okay. So the exercise on grammar will include some manual parsing and some computational parsing, but it will be released tomorrow, right? And it will be due again in 2 weeks. And we will continue with parsing next week on Thursday. And let me check. This will be due also. Syntax will be due in, for syntax, there'll be 2 weeks also, right? As usual, I think.
Yes. Yeah.
Yeah, exactly. Yeah.
And try to keep it that schedule that you have at least 2 weeks to do
Yeah.
one
I
exercise.
just checked with our schedule and 2 weeks. Okay, any questions? Any other questions? And if not, then we could close for the day. And this will be useful for next time, for next week, for parsing. So next week I'll talk about different approaches to parsing. I will briefly talk about chart parsing and a different approach known as shift-reduced parsing. They are quite different and they lend themselves to parsing different types of grammars. Okay. If there are no questions, I think we could finish for today. Okay.